So we're going to look now at 4.2, wave characteristics. And the first thing we're going to do is define what a travelling wave means. We're going to learn some terminology to describe a travelling wave. We're going to identify the main features of a travelling wave, and there's going to be some simple, and I mean simple, calculations using the idea of period, speed, and frequency. Many examples of waves. These are just some of them. Water waves, sound waves, seismic waves, light. These are all examples of what we call travelling waves. The definition of a travelling wave is a disturbance travelling in a medium. A wave is initiated by a vibrating object or something that will create a disturbance in the matter, and then travels away from the disturbance. So in the case of this water droplet, the water falls in the water, creates a disturbance. The waves then move away from that original disturbance. There are two concepts in a wave to think about. One is the particles in the medium. So the actual individual particles of the water. And then there's the wave itself. Now, what actually is a wave? A wave is a transfer of energy and momentum. Okay, so as a wave is moving, the particles are oscillating and the wave is moving through the medium. The transfer of the energy is through the medium. So you could say a quick definition is simply a transfer of energy from one place to the next. Now, what exactly do we mean by this transfer of the medium or the particles being different to the actual movement of the wave? Well, we can conceptualize the particles like a spring and the wave like a pulse moving through it. The individual coils of a spring are like the particles. And as the pulse moves through the spring, the individual particles move up and down, but the actual wave itself moves through the whole spring. You can see it in this small diagram here. This is a string which is through which a wave is passing through. You can see the wavelength of the wave indicating how that wave is moving. But if you look and you focus on one small red dot, the individual particles of the rope or the string are moving up and down, right? So the particles that are carrying the wave are oscillating about a central point, but the wave itself is moving across, affecting all of them. So hopefully that will allow you to conceptualize the difference between what the particles of the medium are doing and what the wave itself is doing. This is a much better diagram where you can individually identify the oscillating particles up and down around a fixed point. Now, this is just a single pulse. The kinds of waves that we're considering are continuous waves, so they would be equivalent to a series of periodic pulses. Now, this kind of wave, or travelling wave, is what we would call a transverse wave. A transverse wave is a wave where the particles are oscillating, but perpendicular to the way that the wave is travelling. Now, examples of a transverse wave are water and light, or what we'd call electromagnetic waves. A different kind of wave is a longitudinal wave. Now, what happens in a longitudinal wave, the particles are oscillating, but they're no longer oscillating perpendicular to the motion of the wave. The pulses are now moving along the same direction as the wave. So what you're getting is a series of compressions and what we call refactions as the wave pulses through the spring in this example. Longitudinal waves include sound and some earthquake pressure waves called P waves. Here we have an example of a longitudinal wave. As you can see, the individual vibrations are along the same line as the wave itself. A transverse wave, again, the movement of the individual particles is now up and down, and it is perpendicular to the motion of the wave. Those definitions are very important, so please make sure that you've learned these. Transverse wave oscillating perpendicular to the direction of energy transfer. Longitudinal waves, particles oscillate parallel to the direction of energy transfer. So this is a water wave, and this is a perfect example of a transverse wave, a single disturbance which makes all the subsequent particles vibrate up and down, but the water is transferring the energy perpendicular to the movement. Here it is again. The particles move up and down, but the wave moves perpendicular. Seismic waves are another really good example of longitudinal and transverse waves. There's a few kinds, primary, secondary, Love and Rayleigh waves, but primary and secondary really allow you to understand the difference between longitudinal and transverse. Longitudinal waves, P waves, you can see here, involve the backwards and forwards vibration of the Earth, basically, to carry that seismic wave. Here is a longitudinal wave. You can see the perpendicular motion of the individual particles along the same line as that wave. S waves are way more dangerous because the particles, the Earth, are actually moving perpendicular. As you can imagine, those cause much more damage. Now let's look at the different wave terms. Some of them you'd have come across before. The way to represent a traveling wave is once again using a graph. But this time, there are two kinds of graphs to consider. This graph is a displacement distance graph. It's almost as if you were taking a photo of your graph. You're seeing all the different particles in the wave with respect to their original position. So you would have the x-axis in meters showing you distance from the original or the origin. So this would be your origin of the wave, and this would be distance from it, and your displacement. In this case, it looks like a transverse wave, but it could be a longitudinal wave. This displacement doesn't just have to be in the y direction. It could actually be in the x direction too. That's something to consider. So what do we use these graphs for? We identify some important parts of the wave. The amplitude of the wave is the maximum displacement, and it can be from the equilibrium position to the top and the equilibrium position to the bottom. These two distances should coincide. The wavelength is the distance for an entire cycle, or a distance from one point in a wave to the next point in the wave. So the same point in the next wave. So as you can see here, if we start at the top, this top point is called the crest, by the way. So if we look at the distance from the crest to the crest, that will give us our wavelength. So this is your first type of graph then, displacement, distance graph. And you can always read wavelength and amplitude straight from these graphs. Now I'm going to quickly reintroduce some ideas from 4.1. We can also look at the time period, and you should remember that time period is the time taken for one complete oscillation. It also applies to travelling waves. The time period of a wave is the time taken to complete one entire wave, or for one entire wave to travel. Frequency then is the inverse, the 1 over period. And we define it as the number of complete waves to pass a point. So here you can see if this is a photo that's taken of 1 second, for example, it would have a frequency of 1, 2, and a quarter, right? So in this case, 10 seconds, if t equals 10 seconds, then you can see there is 1 wavelength, 2 wavelengths, and a quarter. 2 and a quarter wavelengths. Frequency, by definition, is the number of complete waves to pass a point per second. Let's have a look at this particular situation. This is a time period of 10 seconds. So it takes 10 seconds for this entire wave to travel. If we take a picture, a photo of the wave, this time is 10 seconds. See if you can work out the frequency, which by definition is the number of waves to pass a second. Stop the video and figure it out. So what we can see here is that in 10 seconds, 1 wave, 2 waves, and a half have managed to pass. So they've traveled from here to here. So that's 2.5 waves. It's taken 10 seconds to do that. So in 1 second, 2.5 divided by 10 gives you a frequency of 0.25 Hertz. Time and frequency are a reciprocal relationship. So 1 over t gives you f, 1 over f equals t. Very simple relationship to use. The second type of graph is the displacement time graph. Now this gives you the motion of a single particle. So if you look here, maybe one of the water particles, the one in the center, what its motion is over time. As you can see, it moves up and down. So this is a graph of the motion of that one particle. Time period and amplitude can both be measured from one of these graphs. The amplitude from the center to the maximum or the minimum positions. And the time period is simply the time for one entire wave. Here we can see that the time period is 2 seconds. It's always very important to check the units of the axes. So let's put all these ideas together in something called the wave equation. The wave equation tells you the speed of the wave as it's traveling through the medium. So in this water wave, again, how quickly is the pulse moving? So if we look at that entire pulse, what is that speed of the crest as it moves across? Now, its speed is equal to the frequency in hertz, which remember is another way of saying s to the minus 1 per second, seconds to the minus 1. Frequency times wavelength. And wavelength, lambda, don't think I've introduced the symbol yet, lambda is in meters. This is a really super important equation. And it's a super important equation, but easy to derive. Because if we think about it, speed equals distance divided by time. We're using that abbreviation because we're talking about acceleration equals 0, constant motion. If speed equals distance over time, well, what distance are we considering? Well, let's consider a distance of 1 wavelength. How long does it take 1 wavelength to move through the medium? It takes 1 time period, t. So speed equals lambda wavelength over t. And t is equal to 1 over f. So if we plug that in, lambda over 1 over f, we end up with the wave equation of speed equals frequency times wavelength. And that's it. If we go back to our objectives, you know what a travelling wave now is, you know the correct terminology, you know the main features of the wave, and you can do simple calculations. Well done.